session of this conference. The last will be a panel discussion after lunch. So allow me to invite the session chair, Soumitro Banerjee, my co-conspirator for this conference, to chair the session.
Thank you very much, Ritesh. This session will be on the wave function psi. It's bordering on philosophy of science. Wave function psi, ontic versus epistemic debate. I hope the speakers will start by explaining what ontic is and what epistemic is. And yeah, this is I now request Professor Guruprasad Kar from Indian Statistical Institute to start.
Hello. I'm audible? So first, let me thank Professor Banerjee, Ritesh, Manav, Manik, Dipankar for organizing such a conference, which is completely in a new mode, and I like it. Firstly, I was thinking what shape it will take, but now I see that it is very good. People are participating in a discussion in such a way that, yeah, I highly appreciate. And in particular, some of you may not know that Professor Banerjee is not only organizing such conference, but he is one of the leaders in the movement against pseudoscience, and he has so many publications and other things that you may collect. But anyway, let us come to our subject. So I have not prepared any slide because number is going up. What is epistemic and was it ontic? So epistemic and ontic, these two terms are philosophical terms. Like ontology means it refers to reality. It's theory about reality. It's theory about something which exists independently of our consciousness. And epistemic theory means it is about knowledge about the system. But throughout the discussion, you will understand more what is epistemic and what is ontic. Now let us come to the brief description of quantum mechanics. So all we know, quantum mechanics is described by some Hilbert space, and the state is vector, observable as Hermitian operator, and you know that it is self-adjoint operator, so it will have some eigenvalues and eigenstate, and you can express them in terms of projection operator. Now, measurement result is one of the eigenvalue. This is sometimes is not stated in our textbook, that it is the principle that you tell that measurement cannot be other than eigenvalues. Now, when we prepare an ensemble of psi, so all the states are same. I can prepare many copies of psi. This is allowed. And bond probability tell that if you measure this observable A on all of them, then you probability of getting the ith result is given by this bond probability, which is they have this expression. And there is one more thing, that after the measurement, the state will collapse. And in our discussion, this collapse may not play any role, but this bond probability will be very important. Now, if you look at the Copenhagen interpretation and what Einstein thought, if you compare, now we come to Bohr's statement. He's telling it is wrong to think that the task of physics is to find out how nature is. Physics concerns what we say about nature. Then we come to Pauli, even a stronger statement. Observation not only disturb what has to be measured, they produce it. We compel the electron to take a definite position. We ourselves produce the result of measurement. Question of reality independent of measurement is denied by both these statements. Here, psi only represents a pattern of the result for some future measurements. So, in some sense, for Copenhagen, psi is also epistemic. Psi has epistemic nature, but epistemic nature about what? About future measurement. Epistemic, not knowledge about something existing independent of my consciousness, not that way. It is epistemic, but it is knowledge about future measurement result. The fact suggests that Einstein, I have taken from Harrigan and Spakens, quantum states are, but Einstein used to believe that quantum states are solely representative of our knowledge. Psi has nothing to do with the actual reality. Psi is not a part of reality. Part of reality is something like particle has position, momentum, speed, etc., etc. And psi will give us some distribution. Maybe Einstein has not made such a statement directly, but from various discussion, if you extract, then Einstein most possibly used to think that psi has completely epistemic nature. Now, von Neumann proved in 1932 in his textbook, which is known as, which is entitled is The Mathematical Foundation of Quantum Mechanics, where he has proved that you cannot have dispersion-free state. That means you cannot have a state where all the observable will have definite value. I was trying to understand this thing when I entered for PhD, but because of my weakness in mathematics, I immediately could not understand the proof of von Neumann, though it is not very difficult proof. But I was thinking in a different way. I was thinking that, okay, if I take many copies of 0, then if I am concerned with sigma z only, then I can tell all of them has sigma z is equal to 1 value. Because if I perform the measurement, then I will get sigma z with 100% certainty. Now, von Neumann is telling that, no, you cannot assign definite value to all the observables. Then I was thinking that if I have a picture like this, that if I prepare an ensemble like this, then an alternative picture can be given like this, that for all of them sigma z is equal to 1, but for half of them sigma x is equal to +1 and half of them sigma is equal to -1. That means every individual particle has definite value for both sigma z and sigma x, but this for nature is such that if you prepare this kind of ensemble, then distribution is this, that half of them will have sigma x value is equal to +1 and half of them sigma x is equal to -1. I was thinking how measurement will tell, statistics will tell that this is wrong picture. And not only that, if you tell me other measurements, some arbitrary sigma z measurement, then I will look at the probabilities and I will assign accordingly. So I will go on, and for every observable, for every sigma, I can assign a definite value, and this Born probability cannot tell that it is wrong. But so as I was feeling how von Neumann could prove such a theorem which tells that dispersion-free states is not possible, at least for qubits. Now we are coming to formal hidden variable theory model, and I am not going to details of this division among this hidden variable theory model which Professor Leifer may discuss. But psi supplemented means psi is a part of the reality. So psi supplemented model will be like this, that psi is not complete. Maybe you add one more parameter and that is lambda. So this is quantum picture, but actual picture will be like this, that psi, you are preparing all the states in psi, but actually some particle will be prepared in psi lambda 1, some particle will be prepared in psi lambda 2 in this way. So there is another parameter which may be unknown to us. And in terms of that parameter, actually the states are different. And lambda psi decides the value of all observable. But of course there is a constant. Constant is that whatever value psi lambda assigns, it has to be one of the eigenvalue. And to be compatible with quantum mechanics, so this lambda will have some distribution which may depend on psi, may not depend on psi, but in general we will assume that it may depend on psi. So finally you have to, so there is a distribution of lambda, then finally integrating over lambda, you have to reproduce quantum mechanical bond probability rule. So there is one constant that one of the, it has to value has to be one of the eigenvalue, and secondly you have to reproduce this bond probability rule. If you can do it, then you can tell that yeah, it's working. And also you can have some other model where it is called psi epistemic model, where these lambdas are only the actual state which can determine the value of every observable, and psi has no role. Psi has no role to play to determine the value of the observable. Then what is the role of psi? Psi determines the distribution of lambda. This can be another model. And same constants are there. It has to be one of the eigenvalue, and lambda will determine this value of the observable, but finally you have to reproduce quantum mechanics. So it is the comment by John S. Bell, it's not just flawed, it's silly. It's about von Neumann proof. So von Neumann claimed no to the possibility of dispersion-free states, as I told earlier. So von Neumann put some conditions. One of the conditions is something like this: A plus B is equal to C, where A, B, C may commute, may not commute. Von Neumann imposed this condition that every theory, it will give some probabilistic theory, then it has to satisfy this condition. That you take a state of that theory and you calculate the average value of A, average value of B, and average value of C, then this condition has to be satisfied by that theory. He put this condition as being the state of the theory. Now, when we consider hidden variable theory, which may be either psi lambda theory or only lambda theory, then if you apply those theory, then if you calculate this average, it has to be one of the eigenvalues. If you prepare that hidden variable state, then if you calculate the average in that state, then it has to be one of the eigenvalue. That means von Neumann's condition reduces to that eigenvalue, some eigenvalue of A plus some eigenvalue of B has to be equal to some eigenvalue of C. But this is not a verifiable condition when A, B, C are non-commutating. So this claim is unjustified. But not only that, why it's silly you can look at. So verifiable condition is this thing. This I can verify in quantum mechanics. I can perform the measurement, take average, and verify whether this condition holds. Now, every hidden variable theory has to satisfy this condition. So satisfies this condition means satisfying this condition, because this hidden variable theory has to reproduce all these average value of A, B, C by this formula. And finally you get this thing. Now this is 0. Von Neumann is claiming things in the bracket has to be 0 to make it 0. This is very silly. Integration of fx dx is equal to 0 implies fx is equal to 0. This is silly. It may be a sufficient condition, but hardly a necessary condition. And von Neumann made this silly mistake. And for a long time, people that maybe some scientist in 1935, Reed Herman, she pointed out, and maybe some other people pointed out, but it was not recognized.
So f of x is not positive definite.
Yes?
Yeah, so if it was positive definite, then...
Yeah. Now, let us see how actual model for quantum, actual hidden variable model for quantum mechanics can exist. So, if we look at the statistics for spin measurement, every qubit state actually, if you take only pure state, is eigenstate of some spin observables. So every pure state can be represented by this projection, one-dimensional projection operator. But here everything is constant, so n, you can just tell that my state is n, because sigma x, sigma y, sigma z identity, they are constant thing. So you can tell my state is n. And if you measure in some direction some m, if you measure the spin along some direction m, so these are the probabilities, this Born rule. So it is very beautiful that finally you get the thing in terms of scalar product in R3. And if you calculate the average, you can. So here, this is actually calculating the average and calculating the probabilities are same. Both are function of n dot m. And so Bell first provided a model, most possibly in 1964, early 1964, but it was published maybe after 2 years in 1966. But this is not exactly Bell's model, it is even simpler than that. Here completed state is, of course, it is psi supplemented. There is psi, but there is another variable. For Bell, it was a vector. But even you can take it to be a scalar. And this scalar can take value from this region, -half to +half. And as I told you, that distribution of lambda in general may be dependent on psi, but here the model does not need that. The distribution is uniform. And definite value for completed state is, the formula is something like this. The sign function is like this. So it will be either +1 or -1. So spin value is always +1 or -1, that is reproduced. And actually, you can calculate the average value for state n and measurement direction m. You can reproduce the quantum mechanical values. It's just some steps. And it is very beautiful, everyone can do it. Because for Bell it was vector, but this is simpler model. So indeed there is a model which can reproduce quantum mechanics. But there is another model, actually it was in Koch's paper, but people did not give much importance to it, but Professor Spekens actually discussed it in an elaborate way. This is a nice model. Here, this n does not, n means a state, quantum state, does not play any role in assigning value to the observables. So value of observable is completely given by m, completely given by lambda. Here lambda is a vector, lambda is not a scalar. Lambda is a unit vector. And distribution of lambda is given by this, where this function, for x greater than 0, it is 1, for x less than equal to 0, it is 0. And it also, it needs some mathematical calculation, but you can check that it also reproduces quantum mechanics. But this model has something beautiful properties. For two different quantum states, psi and phi, there are common ontic states. Because actual ontic state does not depend on quantum state. So if you take two non-orthogonal states, then they will have some common region where there will be ontic state in both the distribution. This can explain why non-orthogonal quantum states cannot be reliably distinguished. We know that in quantum theory, two non-orthogonal states cannot be reliably distinguished. Here you can explain things, that why you cannot, because if the state comes from this region, then you will not be able to tell whether it is psi or phi. This is very natural. This is like classical probability distribution. This picture can also provide a solution to the notorious collapse postulate by giving the post-measurement state as a updating of probabilities. In classical world, something we don't know, then when we know something, then we update our probabilities. It's like just like that. So it solves the measurement problem for which we are fighting with each other for a long time, and so there are so many theories. But there had been a water. There had been a big development in this direction in 1957 when Gleason proved a theorem, which actually does not suffer from some assumption which cannot be acceptable, like in von Neumann's case. Here the theorem tells that you consider Hilbert space and you consider all possible projectors, collection of all projection operators, and you define a probability measure on these projection operators, and it satisfies this thing. It's like probability should be bounded by 0 and 1, on identity is 1, and if PIs are orthogonal, then this holds. Now, Gleason proved that if dimension is greater than or equal to 3, then there exists a density operator, there always exists a density operator. So whatever probability measure you define, I will get a density operator. You cannot find a probability measure for which I will not get a density operator if the dimension of this Hilbert space is 3 onwards. But already in 2 dimension, we have got some probability measure which is not reproducible from density matrix. So in so that in theorem also you see that for 2 dimension it does not apply. So there is a scope that you can, and indeed there is. So I am making a comment which will be clear after in next some slides. So measurements contextuality in some sense was discovered in 1957 itself, though it was not appreciated before Bell put the question with glaring clarity during 1964 to 1966. Why I am telling this thing? Gleason never thought that this P may belong to different measurements, but he is assigning same probability measure on them. It is kind of non-contextuality which he did not appreciate. Because I can write so many measurements. P may be member of this thing, member of this, but this thing I am putting same. So this is kind of non-contextuality which actually he was a mathematician. Maybe Gleason was a mathematician, I think. Yeah, he did not appreciate. He thought it to be natural. So let us come to the question of contextuality, non-contextuality. Consider let is a 3-dimensional Hilbert space. So consider a projective measurement where P1 plus P2 plus P3, which is projected on phi 1, phi 2, phi 3, phi 1, phi 2, phi 3 are orthogonal set. Then it is a measurement. But you can define another projective measurement where P1 is common. Because what you do, you take phi 2 and phi 3 and consider these 2 states. Phi 2 plus phi 3 by root 2 and phi 2 minus phi 3 by root 2 and name the projector Q1, Q2 as projector on this thing and Q3 as projector on this thing. Then this is another measurement. First measurement is P1 plus P2 plus P3 is equal to identity. Second is P1 plus Q2 plus Q3 is equal to identity. Now, you are going to, so in hidden variable theory, you are going to give a definite value to the projector, which can be either 1 or 0. Now, you have to decide So if this is B1 measurement, this is B2 measurements, and measurement in B1 and B2 are measurements of B1, B2 are different in general. A HBT is called non-contextual if it assigns value to observable in a context-independent way. That means independent of other observable along with which it is measured. So in this particular case, actually, earlier, when Kochen-Specker originally proved, he took a spin 1 particle and considered 3 observables like this: S(x) square, S(y) square, S(z) square. But the same thing can be done in terms of projector for 3 dimensions. Now, contextuality, non-contextuality means in whichever measurement this particular projector P1 appears, you are going to give it same value. This is non-contextuality. See, quantum mechanics deals with probability, but quantum mechanical probability is also same. So quantum probability is also non-contextual because it is trace of rho P. It does not care P belongs to which measurements. It does not care. But the same kind of thing when you are going to a hidden variable theory where you are giving to give definite value to observable, here also you are using the same thing, that my value assignment will be non-contextual. Then actually you can understand that Gleason's theorem is a general theorem. So what kind of probabilities you are giving, it does not care. It tells that if the dimension 3 or more, then rho is the only solution. Then of course you cannot assign definite value to all possible projection operators, because for every rho you can have a projective operator such that this is neither 0 nor 1. This is always possible. So in some sense, actually, Gleason proved this non-contextuality, but interesting part of Kochen-Specker theorem and theorem like this, that they do it for finite number of projectors. And in particular, in 1967, Kochen-Specker using 117 vectors could prove that quantum mechanics is contextual. But interestingly, in 1996, I forgot to give the reference, Adam Cavallo could do it, but in higher dimension, in 4th dimension, he could choose 18 vectors and could prove the same. So rule of the value assignment means for every projector you give either 0 or 1, but I am using this symbol instead. This symbol is bigger, so I am using this symbol for the same meaning, and the sum of these things should be 1, where this pi I form a orthogonal basis. And then a very elegant, interesting proof. These are orthogonal sets: phi 1, phi 2, phi 3, phi 4, phi 1, phi 5, phi 6, phi 5. In this way, you can have 9 orthogonal bases. And if you give definite values, so that see where contextuality or non-contextuality plays the role, this V phi 1 and this V phi 1 is same, but they are actually in two different measurement contexts. But you are giving the same value, which can be either 1 or 0. Now, if this equation has to hold, then there will be contradiction, because if you add the left-hand side, this thing V phi 1 or V phi 2, they have appeared twice. So left-hand side will be even, and right-hand side it will be odd. We showed that non-contextual HBT in general cannot reproduce quantum mechanics. Even we did not invoke any quantum state to prove it. Just from the observable, you can show that it is not possible. But there are other proofs where even less than but this is very interesting. This is due to Leifer and Specker. But this psi-epistemic theory makes our life very simple. So if you consider two non-orthogonal states, phi and omega, and again there is a mistake, there may exist some lambda, there may be some psi-epistemic theory where there may not be some common lambda, but I am assuming that At least there is one lambda which is common to the distribution produced by psi and distribution produced by omega. We consider such HBT state lambda and observe the following. For this HBT, if you take this lambda which is coming from this common region, for this projector it should be 1, and similarly for this projector also it should be 1. Now you come to this. This state I have taken this, sometimes I have made some mistake. Yeah, sometimes this is psi omega, this is psi phi. So I have made some mistake. So actually it is 3-dimensional and the states are 1 plus 2 plus 3 by root 2, 1 plus 2 minus 3 by root 2. One of them is omega, one of them is phi. And as they are non-orthogonal, I assume that there is a common ontic state which I am considering, and for that ontic state, this projector will get value 1. This projector will also get value 1. Now,
may I just quickly say the proof is actually due to Rob Clifton. I don't want to take credit for something we didn't do. This is actually due to Rob Clifton.
But maybe this thing he didn't.
No, he did that.
Huh?
He did that, exactly this proof.
Oh, exactly. I thought that he might have missed this psi epistemic character.
We can talk about that. I don't want to interrupt the talk.
Yeah. So this is 1, but in the orthogonal set, one of them will get 1 and others will get 0. So if this is 1, this is orthogonal to this thing, so this is 0, this is also 0. Similarly, this is 1, so this will be 0, this will be 0. Now you consider this orthogonal set. These two are 0, so this has to be 1. These two are 0, this has to be 1. Then you are going to a contradiction because 1, 2 are orthogonal, but both of them are getting 1 instead, where one of them should get 1, other should get 0, but two orthogonal projections are getting value 1, equal to 1. This is a contradiction. So you have used a very less number of vectors. So how many? Maybe 8, no? Actually, I have not read the Clifton's original paper, so I got it from your paper. And Spakens actually, in 2005, enriched the subject to discover another form of contextuality in quantum mechanics, which is called preparation contextuality. And interestingly, this preparation contextuality can be proved in qubit itself. Whereas measurement contextuality, at least for projection operator, you cannot do it in 2 dimension, but for preparation contextuality can be shown. How much time do I have? Oh, then I have to be very.
You can look at that.
Yeah. I am not going in details, but preparation contextuality actually same quantum mixed state can be prepared in so many ways. Like here, you consider a density matrix rho n, then it can be prepared in 1,000 ways. So what you do, you take some of the preparation possibilities and you. I am not going in details because then, so you use the preparation non-contextuality assumptions, but they have to, for orthogonal states, they have to satisfy this condition, and finally you can show that there is contradiction. So there is preparation contextuality even for qubit. Now, I was a little bit happy that we have a case, Kochen-Specker model, and in particular, Spakens constructed a theory, psi-epistemic theory, which is not quantum mechanics, which is not non-local and contextual, but he could reproduce almost all the interesting quantum information processing. Maybe you are going to discuss that things, yeah. So I was very happy, but in 2000, this is in 2012, maybe 12, yeah. something very shocking things came this by Podol's, Pusche, Barrett, and Rudolph. They told something very elegant proof to discard psi epistemic theory. How did they do it? You consider two quantum states, 0 and plus, which are non-orthogonal. So if you go to their probability distribution for lambdas, then the picture will be like this, because there will be some intersection region. And I already told you that this can explain why you cannot reliably distinguish two non-orthogonal states. So it is expected that when the ontic state lambda comes from the red portion, one will not be able to distinguish the quantum state. So we are happy with this picture because it explains things. But now we consider two sources, and each source produce either 0 or plus. This source also produce 0 and plus. And so what are the possible preparation? 0, 0, plus 0, 0 plus, again 0 plus and plus plus. Now in psi epistemic picture, what are the possible ontic state? It will be some lambda 1 will come from here, some lambda 2 will come from here, so probability of lambda 1 and lambda 2 at their independent source, so it will be mu of lambda 1 into mu of lambda 2. And our common sense accepts this thing, that okay, things will be like this, because in classical world, if there is some box where there is some red ball and black ball with some proportion, and in some another red ball and black ball with some proportion, you take two balls from randomly from there, then their probability of getting will be like this thing, probability of this thing into probability of this thing. So it seems to be natural. But now there is a possibility that if you look at the ontic picture, then sometimes it may happen that the lambdas that are coming for this first source, lambdas are coming from this region and lambdas are coming from this region, both from red region. It might happen. Then actually we can tell that if lambdas come from red region for both the cases, then we should not be able to discard even a single quantum state. That means we cannot tell, we cannot tell that at least this state was not given. This should not happen. But in quantum mechanics, after getting these two particles, you have bigger scope. You can perform some measurements which is very non-classical. You can measure them in Bell basis. It is a different kind of Bell basis. You have to be very careful. It is not just 0, 0 plus 1, 1, 0, 0 minus 1, 1. It is 0, 1, 1, 0, 0 minus 1 plus. So it is a little bit different Bell basis. But it has a beautiful property. If you measure in this basis, then if it is the result, then you can tell, no, 0, 0 was not given. Because you can check that these two are orthogonal. If this is your result, then you can tell, no, this one was not given. And in every case, you can discard at least one state. And if you believe in epistemic picture, then at least sometimes you should fail. But in quantum mechanics, always you pass. So though, at least if you look at the Cochin-Sprecher model, it's passed the first test, reproducing bond probability. I took a second test where it fails. Because if finally a psi epistemic theory can replace quantum mechanics, it has to reproduce all quantum results. But of course, it passed the first test, but PBR posed a different kind of test, and psi epistemic theory fails. And there is another result which has been nicely discussed by result is due to Kolbach and Renner, and it has been discussed in details by Leifer in his review paper. It tells that, okay, I only consider those signaling, which Leifer has called parameter independence. Like in Bell's theorem, deriving Bell's theorem, you take two things, parameter independence and outcome independence. So you assume only one, parameter independence. Then, but if someone asks, any parameter independence theory can reproduce quantum mechanics, it is meaningless question, because quantum mechanics itself is a parameter independence theory, but means it respects no signaling theory. So the question is not very meaningful question. But I can make the question meaningful if I tell that, okay, if I take entangled state or two-party system, then I want that my local marginal things differs for given lambda, it differs from quantum. If I claim whether this kind of theory can be produced, that it will reproduce quantum mechanics, this is one claim, but at the same time, for given lambda, these local measurement results will differ from quantum mechanics. And it has been shown, it is very difficult because you have to consider so many measurements on analysis side, so many measurements on Bob side, and there is a chain Bell-Cell equality by which they could prove that no. For every, so if you consider the maximally entangled state, for every lambda, whether lambda includes psi or does not include psi, it is always half. That means you can, in local measurement results is same for quantum mechanics as well as in lambda theory. So lambda theory does not give any different results other than quantum mechanics. There is a great consequence, again discussed by Leifer, great, because after this paper, Kohlberg-Schreiner discussion went in a different direction, which I don't understand much also. A great consequence of CR results, this Kohlberg-Schreiner result, if you consider phi plus and 0, 0, if you look at for phi plus, probability of down result is half for all lambdas in its support, because Kohlberg-Schreiner has proved it. If you consider 0, 0, probability of down result is 0 for all lambdas in its support. Then, if you consider some psi epistemic theory, then for phi plus the lambda distribution, or mean the epistemic state, and the support of this epistemic state and support of this epistemic state, epistemic state of this quantum state 0, 0 and epistemic state for this phi plus, they should have disjoint support because of this. Because if there is a common lambda, then we will get again contradiction. To my knowledge, I may not be correct because there are so many posters, I have not seen all of them. But to my knowledge, this is the first time one could show without further assumption, accepting parameter independence or no signaling, that two non-orthogonal states are ontologically distinct. But I don't know very recent result that whether, of course, Leifer shows a long range of states which are ontologically distinct. I am taking an extreme case. Now, I will end with two things, some questions on my philosophical position. Question I am putting, which will be discussed maybe after our tea. How to see the preparation independence assumption of PBR results? Because after PBR result, very elegant result, but there has been much criticism about preparation independence, like probability can be factorized that I showed. Does psi epistemic theory really solve the measurement problem? Because we like psi epistemic theory, but because measurement problem is not a problem in this theory. But there is a paper, I forgot the writers, who has tried to show that in the existing psi epistemic theory, there is measurement problem cannot be solved. what is the final implication of Kolbeck-Renner result? One thing I told, but Kolbeck-Renner is claiming that epistemic theory is gone. Or not only that, even supplemented theory is also gone. Hidden variable theory itself is gone. His claim is very weak. How true it is. Now I am coming to my philosophical position, which almost coincides with Professor Gisin. I am materialist, and hence I believe in the existence of matter independent of our consciousness. I do not reduce matter to the sum of sensation as preached by positivists like Mach, because at some point of time Mach used to tell that you cannot tell matter exists, but of course you have sensation, so you can give a combination of this sensation. You can tell it as matter, but that does not mean something exists independent of your consciousness. And Lenin fought against this kind of idea, and he wrote a book, possibly Materialism and Empirio-Criticism in 1909. The properties of matter belongs to the category of science, and hence I am not afraid of if rules of nature say that quantum particle may not possess definite position and momentum. Here I differ with Einstein, because Einstein also took a materialist or realist position, but to him, existence of particles means along with its position, definite position and definite momentum. But I am giving up this. If science says that it may not be possible, I am not afraid. To me, so finally to me, psi is of course a function of something. And it may be very peculiar. But that's something that exists independent of my consciousness. Okay, thank you for your patient hearing.
Thank you very much, Professor. Is your now it is Professor Leifer, who comes from the Chapman University. He did his PhD in University of Bristol, and he has been associated with the Perimeter Institute also, and now he is with the Chapman University. I request Professor Leifer to start.
Thank you. Can everyone hear me okay? Okay. I'd like to start by thanking the organisers for giving me the opportunity to speak here. I'd also like to thank everybody who has showed us great hospitality since we've been here, including all of the student volunteers and everybody who helped out. I also would like to thank the previous speaker, Professor Kar, because he's covered some of the background that I need, and that means that I'll be able to spend more time in the talk on jokes, which is important. So I also like to start my talks with something local. So we're partly here to celebrate 100 years of Bose's letter to Einstein. So I tried to find a quote from Bose that I thought was relevant to this talk, or this whole area. So this is from a paper where S. Rameseshan is reminiscing about conversations he had with Bose about 50 years earlier. Okay, so it's probably not word for word exact, but this is what he says. He said, I asked him whether he felt elated or happy or transported when he discovered what is called the Bose statistics. And this was Bose's response. If I were truly honest, I can say no. My feelings were entirely different. Let me put it this way. Suppose you had a severe headache or stomachache, and the ache suddenly stopped. That was the feeling I had. For all the previous derivations gave me ceaseless pain. If you call cessation of pain as happiness, then I can say I was happy. Isn't this like doing research on the foundations of quantum mechanics? Because we often have this image that's portrayed in popular science, but, people like Carl Sagan and Stephen Hawking, that, we approach physics with awe. We're looking at the face of God or something like that. But no, in quantum foundations, we're annoyed, right? There's this itch that you want to scratch, and you want to try and solve the problems, and the problems have a persistent way of sticking around. So it's very much like he describes, except that in this case, the headache has never gone away completely. So it's 100 years since Bose's letter to Einstein. There's a much less auspicious anniversary, which is that this review article that I wrote is 10 years old. Pretty much, it was published in November 2014, so it's pretty much exactly 10 years old. And this is probably why I'm here today speaking to you about this subject, right? This review article has become my second most cited publication. This was never the intention. It was published in an open access journal called Quanta, which none of you have ever heard of. It's incredibly obscure. If you've read this paper, it's probably the only paper you've read from that journal. This is something I share in common with John Bell as well, because the Bell's theorem paper was also published in a paper in a journal nobody ever heard of. So why is this? Right, so this is my second most cited paper, and it's published in a journal that doesn't even get listed in the citation indices. This was a huge mistake on my part, of course. The reason is that this review article came about for a similar kind of reason that I was just talking about. It was I wanted to solve something that was annoying, right? And also, when I was writing this, I'd just come back into academia from a fairly long break due to illness. And I was only working part-time, and I was pretty sure that I was going to be leaving academia immediately as my position at Perimeter Institute ended, right? So I didn't really care where I published it. And the editor of this journal came to me and said, could you write a review of the PBR theorem? And, since the PBR theorem was published, there was a lot of literature on it, and I sort of wanted to set the record straight, right? This is something that I cared about, so I wanted to sort of do the definitive take on it. So I think the editor of the journal thought that I would write a fairly short paper that was sort of a bit like the blog post that I wrote about the theorem back in 2011. And instead, I turned in 100 pages, because I really thought while I was writing this is probably the last paper I'm ever going to write. So I want to make sure that I explain all the background. I want to make sure that the math is really rigorous, and I want to make sure that I go through every criticism that was in the literature so far. People come up to me and say they've read this article, and I apologize for that because it's over 100 pages long. And so I admire all the people who've told me that they've read it. Really, I think I could do a much better job of it if I started again today. Anyway, the point of this story is just that, somehow when you do the things that you're passionate about and you don't care about who's going to read it, you end up doing the stuff that has the biggest impact. At least that's true for me. All right, so I'm going to recap some of the things that were already discussed quickly. It doesn't hurt to see the definitions again quickly. So the first slide is what is ontic versus epistemic. Okay, so I'm not going to belabor this. I will make one complaint, though. Some people, instead of using the word psi-epistemic, you'll see this quite a lot, will talk about epistemic theories. They mean psi-epistemic theories. The qualifier is very important. All our physical theories are epistemic. They tell us what we know about reality. Okay? But psi-epistemic, specifically which objects in the theory are epistemic, and specifically the quantum state, that's very important. I also want to say here that in this talk, I'm only going to consider realist implementations of this. So in the ontological models framework. Now, if you're a psi-epistemic person, probably the most popular route to go these days would be to be something Copenhagen-like, right? And that doesn't fit into the kind of framework where we prove these results. However, as we heard about yesterday, things like the local friendliness theorem, so these extended Wigner's-Friend results, they do have implications for Copenhagen-like interpretations. And guess what? I have a review article about that as well. And one of my co-authors on that review article is in the audience, Ilay Ying, and she told me that I had to mention the review article so that you would all read it. So if you're interested more in the Copenhagenish side of things, that is, I think, a very interesting subject to get into these days. Okay, so just to back up, in classical physics, the distinction between what's ontic and epistemic is fairly clear. So say you consider a single particle, we consider the ontic state to be the point in phase space that it occupies. And what that means is that all of the things that we think are objective intrinsic properties of the individual system are determined by this ontic state. The energy is a function of x and p, for example. So you specify that, then you specified all of the objective physical properties of the system. A classical epistemic state is going to be a probability distribution over phase space, and it's what you're going to assign if you don't know exactly which phase space point is occupied. Okay? So this represents somehow you have some uncertainty or lack of knowledge of exactly what state the particle is in. Now, the other thing I can do, given that I have the time, is do some extra complaining. So I already complained about epistemic versus psi-epistemic. I'm going to complain about this term epistemic state here as well, because it's caused a lot of confusion. It doesn't matter that this is, that I think a probability distribution is epistemic. Like, I'm a Bayesian, and I think probabilities represent knowledge, and that's it. Okay? But that doesn't matter for this debate at all. What matters is the distinction between something that's an intrinsic property of an individual and something that is probability-like. So like a probability distribution in classical mechanics. So for example, if you're a frequentist about probability, you're going to talk about a statistical state, or an epistemic state, or an ensemble state. Okay? For the purposes of what we're doing here, those things all mean the same thing. It doesn't really matter that it's knowledge. It matters that it's like a probability distribution like. It just so happens that pretty much everybody who invented this terminology was an objective Bayesian of some stripe, so for them it was uncontroversial. But in the literature, people will make these distinctions. The knowledge part doesn't really matter. It's that it's probability-like. Okay, so I'm going to briefly talk about some of the history because it's important for setting the stage. Recent history, that is. So for me, the starting point is really, as was mentioned in the last talk, the Speckens toy theory. Okay, so what is the Speckens? Oh, by the way, each of these things has two dates. The first date is the date that the paper appeared on the archive. The second date is the date that it appeared published. And you'll actually notice that as we go through the history, the situation in publishing quantum foundations papers improves, right? So back in the early 2000s, it was hard to get your papers into a decent journal. I think Rob had an awful lot of back and forth to get this thing into PRA. I think he submitted it back in 2004, or maybe 2005. Took a couple of years to get published. As we go on, you'll see that gap decreases. So I guess that's a good thing. Anyway, so Speckens proposed this theory. And it's a theory which is basically a classical theory. It really is classical Hamiltonian mechanics, except there's a restriction on how much you can know. Okay, you're not allowed to know the exact phase space point. There's something a bit like the uncertainty principle, although it's not to be, it is to be interpreted epistemically as just a limitation on our knowledge, not as a, so a finer grained picture exists. The base point really doesn't exist, but we don't know exactly what it is. So his restriction is, roughly speaking, that half of the information it would take to specify the ontic state can be known. Now, the reason why I start here is that I think that this is really the context of the modern debate, right? You have the Speckens toy theory. It has a number of explanations, and what we mean today by a realist psi-epistemic theory is a theory in which the type of explanations that work in the Speckens toy theory hold. Okay? That's what it means to me. This is, in some sense, the canonical example of what a psi-epistemic theory should look like. And so, you know, you need, when you're working on these sort of abstract theorems, you need a very concrete model in your mind in order to prevent you from going wrong and saying things that, you know, shouldn't really hold. Just like if you're thinking about Bell's theorem, many people have said silly things like it rules out all hidden variable theories. It's very handy to know about de Broglie-Bohm theory in that case, so that you don't make mistakes, right? So it's good to have these specific examples of theories in mind. So I will briefly talk about some of these explanations, at least a couple of them. So later on, Harrigan and Speckens come along, and this is where the formal definition of psi-ontic versus epistemic came in. And then, as we heard in the last talk, in 2011, see, there's only a gap of a year here, so it's, the Pusey-Barrett-Rudolph theorem was showed that ontological models that have to satisfy this preparation independence postulate, which we heard about, must be psi-ontic. Other theorems of this sort followed. Particularly, we heard about the Kolbeck-Renner one. There was one by Lucy and Hardy. All of these theorems involve assumptions beyond just the raw ontological models framework. And so a lot of the literature, including in the review article, is about criticism of these assumptions and whether they are really viable or necessary assumptions. Okay, so in light of that, you might want to say, well, let me throw out the assumptions and ask, what can I prove if I don't make additional assumptions? And around the same time, it was shown that without any additional assumptions, there are psi-epistemic models for all finite dimensional Hilbert spaces. Okay, so what do you do in light of that? There's sort of two alternative tracks of work that came out of this. One is to say, well, maybe I don't like the preparation independence postulate, but maybe I can find some other assumption that's less controversial under which I can prove psi-ontology. So there's a bunch of work along that line, along those lines. I prefer this second line of work, which is to say, well, you know what, the definition of psi-epistemic in Speckens and Harrigan is extremely weak. It's not strong enough to require that the theory has the kind of explanations that we have in the Speckens toy theory. So we can propose something slightly stronger and see if we can rule that out. So one reason for wanting to do that is because there's a hierarchy of no-go results. So that, again, in the review article, I discussed this in great detail, but over time, a bunch of no-go results have been proved for realist models of quantum mechanics. And if you look at this hierarchical diagram here, if you were able to prove that the theory must be psi-ontic, then it would have a lot of other implications. I'm not going to discuss what all of these mean, but the point is that it seems very strong. The only thing it doesn't really prove is quotient-Specker contextuality, which is a little bit annoying, but nonetheless, this seems to be close to the top of the hierarchy of things that you might prove about realist theories of quantum mechanics. So if you're trying to understand either, you know, fundamentally what is it about quantum mechanics that's responsible for its strangeness, then looking at the thing that implies everything else might be good. Also, on the other hand, if you're looking at applications of no-go theorems, we have plenty of applications of Bell non-locality. We have some applications of contextuality. But if this is stronger, it should have more applications, you would have thought. Okay. So this is another reason why I'm interested in doing this. But we can't prove this without additional assumptions. And so if I say, well, I would like to prove Bell's theorem by first proving psi ontology and then using these implications, well, that proof would inherit any assumptions that I made up here. So if I can't prove that without additional assumptions, then it's not a good way of proving Bell's theorem because Bell's theorem doesn't require those assumptions. So if I can sort of replace this with something slightly weaker that still has all these implications, that would be interesting from the point of view of understanding the structure of all the no-go results. Okay, so let me briefly talk about Speck and Stoy theory. I'm not going to go into great detail, but in Speck and Stoy theory we have, first of all, ontic states, so states of reality. And in the Speck and Stoy theory, in the simplest system, a toy bit, there are 4 of them. One way to sort of visualize what's going on in the toy theory is to imagine that you have a box. We're looking top down into this box, and we divided the box by the x and y axes into 4 quadrants, and the 4 ontic states, you imagine that there's a ball inside this box, and the 4 ontic states represent which of these quadrants the ball is. Right? So the ontic state plus plus means that I'm on the positive side of the y-axis and the positive side of the x-axis, for instance. So that way I can get 4 ontic states. They're coarse-grained, but that's, that doesn't matter. Okay, so those are the things we're interested in tracking. And then Speckens imposes this assumption that you can only know half of what's available to be known. And under that restriction, these are the possible epistemic states. These are the possible probability distributions you can have. Blue here means 50% probability. So, and under here I've written these sort of quantum-like things. So this notation is supposed to mean it's not really a quantum state, but this is the thing in the toy theory that's analogous to that. So the x plus and x minus states, you're supposed to think of those as the analogs of the eigenstates of sigma x in quantum theory. Okay, so we have these 6 possible states. I'm not going to need to talk about the measurements too much here, so, but that's the key point. And notice that there's overlap. So as was discussed in the last talk, suppose I tell you that the ontic state of the system is here, this back right quadrant here. It could be because I prepared x plus, that would happen half the time. It could be because I prepared y plus, that would happen half the time. It could also be because I prepared z plus. So there's overlap in the space of ontic states. Okay, and this allows, so as was alluded to in the last talk, one of the sort of key explanations that people focus on is the idea that you could explain the indistinguishability of non-orthogonal pure states by saying, well, suppose I either prepare this state or that state, and then I give you the system and ask you which one did I prepare. You won't be able to tell with certainty, because if you find the ontic states here, then it could have been either of these 2. So necessarily, just because the only thing that you're given is the ontic state of the system, necessarily you're going to do no better than guessing half the time. Okay, so you're necessarily going to fail to correctly identify the states with probability a quarter. And the idea is that this could be the explanation for why, or part of the explanation for why non-orthogonal pure states are indistinguishable. I don't know what's happened to my minus signs here, but they're supposed to be there. Now here is another explanation, which people tend to focus on a little bit less in this context. But here's the representation of the maximally mixed state in the Speckens toy theory. Light blue means 25%, so it's a uniform distribution. And you notice that you can obtain that distribution via a convex mixture of x plus, x minus, y plus, y minus, or z plus, z minus. They both all give you the same probability distribution. And so the reason they can do that is because of the overlap, right? If the x states didn't overlap with the y states or didn't overlap in the z states, then there's no way they could give you the same probability distribution, because they would have to give you 3 disjoint supports. But because there's overlap, we can have this property that they give you the same probability distribution. And so here, the explanation of the fact that a mixed state has different decompositions into pure states is that pure states don't really represent things like points in phase space. They represent spread out probability distributions which overlap. And in the last talk, we heard about preparation contextuality. So the assumption that things work like this is basically what we mean by preparation non-contextuality, right? Maximum mixed state, is the same thing operationally. It makes the same predictions regardless of how you prepare it. And so preparation non-contextuality says it shouldn't matter how you prepare it. It should give you the same probability distribution. But that's, again, something that's very natural in the Spekens toy theory. Due to lack of time, I'm going to skip the no cloning thing. It's not so important, but I just wanted to show you that there are different ways in which things are explained using overlap in the Spekens toy theory. It's not just one explanation. People do tend to focus a little bit on the indistinguishability of pure states explanation. Okay, so this next bit I'm going to go through in a rather lightning way. So we're going to talk about ontological models framework. It's basically similar to what was called hidden variables in the last talk, except I make no assumption about determinism. Okay, so we start with just an operational description of some prepare and measure experiments. You have a preparation device with a bunch of different settings. P is your choice of preparation, measurement device, bunch of different settings, and then you have some outcome, which appears on the measurement device. Okay? So what I mean by an operational theory is some way of predicting the probabilities for all these experiments. So I need to have a probabilistic prediction for each choice of preparation and measurement. An ontological model is an attempt to explain those predictions in terms of some physical system that has some real physical properties. So what we assume is that between preparation and measurement, there's actually some physical system that propagates here, and it has some properties that are independent of us, right, called lambda. Lambda is called the ontic state, and it can be any mathematical object you like. Okay, so then what we imagine is that when we select our preparation P, that influences lambda, but doesn't necessarily have full control over it. So you have some probability distribution corresponding to each preparation. And the measurements, they correspond to these conditional probabilities, which are often called response functions rather confusingly, but they're just conditional probabilities. So in this case, we imagine a two-outcome measurement with outcomes A and B, and these lines represent, if the ontic state is lambda, what's the probability of getting outcome A or outcome B of this measurement? Note that these do not have to be 0 or 1, so we have regions here. We have a region here, for instance, where the probabilities are 50-50. And then we say, well, obviously we want this theory to reproduce the predictions of the operational model, and so we would like it to be the case that if you average these conditional probabilities over your lack of knowledge about your initial lack of knowledge about the ontic state, that you would get the operational probabilities. Okay, so I haven't mentioned anything about quantum mechanics yet. Okay, this is the formal definition. I assume somebody will post these slides somewhere after the meeting in case anyone wants to see that, but I'm not going to go through that. Obviously, we're most interested in the case where the operational theory has a model in quantum mechanics. In that case, preparations are going to correspond to some density operators. Measurements are going to correspond to, well, measurement operators, most generally a POVM, but could be a projective measurement as well. And the operational probabilities, if you have a quantum model, are going to be given by the Born rule. Okay? And so therefore, if you have an operational theory which has a quantum model, then an ontological model of that must satisfy this, right? So the ontological model probabilities must reproduce the Born rule probabilities. And that basically is the entirety of the ontological models framework. So when I mean proving something just based on the ontological models framework, I mean just this. Now, those of you who have suffered through reading my review article will note that I tried to be very rigorous about contextuality. which leads to very cumbersome notation. So I'm not going to do that here. I'm going to introduce something that I call naughty notation, because it ignores contextuality. So generally speaking, note that the mapping from a preparation procedure to a density operator and from a measurement outcome pair to a POVM element doesn't need to be one-to-one. I can have different preparation procedures that prepare the same state, and we've seen examples of that. Mix x plus and x minus, mix y plus and y minus, they both give you the maximum mixed state. They're two different preparation procedures for the same quantum state. There's nothing in the formalism that implies that if I have two preparations corresponding to the same density operator, then they're going to give you the same probability distribution. And in fact, preparation contextuality tells us that that can't happen in general. Okay? So you should not assume that. Similarly, for the measurement operators, if you have some outcome of measurement M1 and an outcome of measurement M2 that correspond to the same measurement operator, it doesn't mean they have to correspond to the same response function. And in fact, because of measurement contextuality, in general, you wouldn't. So it is indeed extremely naughty to write this probability measure as a function of the quantum state, rho, instead of p. And it's very naughty to write this as a function of the measurement operator instead of just the abstract description of the measurement. However, you're going to get very cluttered notation if you don't, so I will often do that. But what it really means is if I write down an equation that says u mu of rho, it really means that it applies for all mu of p, which has that as its density operator. So when I'm proving results which sort of universally apply to all preparations of the same state, then it doesn't do any much harm to use that notation. But when you're in a situation where you really have some contextuality that's important, then you won't be able to do that. Okay, so now I can cheat and label my probability distributions by states, which we shouldn't do. But we introduced the notion of ontologically distinct. So this was a bad choice of color, I'm sorry. But basically, you say two quantum states are ontologically distinct is basically about overlap. Okay? So in the ontologically distinct case, there's no overlap between the probability measures. In the ontologically indistinct case, there is. Okay? And then your definition is that an ontological model is psiontic if every pair of pure states is ontologically distinct, so there are no overlaps. Otherwise, it's psi-epistemic. Did I say something? Oh, yeah, okay. So what that means is that if I were to tell you the ontic state, in this case, you would be able to infer with certainty whether rho or sigma was prepared. And so that's the sense in which the quantum state is part of the state of reality. It's like the actual state of reality allows you to infer with probability 1 what the state was prepared. Notice that this notion of psi-epistemic is very weak, as I said earlier. It doesn't tell you how many pairs of states have to overlap, and it doesn't tell you how large that overlap has to be. Okay, so we saw the Cauchy-Specker model. I'm not going to go through it again. Important point is it's psi-epistemic. You have this overlap. In fact, in the case of the Cauchy-Specker model, that overlap is as large as it could possibly be. It's a very nice model from the point of view of this. But as I said, I'm not going to go through the constructions, but there are models for arbitrary finite dimensions that have been published. There's an important caveat, though, right, which is this. If I consider two quantum states that have a fixed inner product, and I look at what happens as I increase the dimension of the Hilbert space to the corresponding probability measures, the amount of overlap decreases. Right? So if you use these models in the limit, you can make that overlap arbitrarily small. So the Speckens toy model explanations doesn't just require that there is overlap, it requires that there's enough overlap to explain, for example, the amount of indistinguishability we actually see. So if you have a pair of states which have a very large inner product, and they have a very small amount of overlap, that's not good. So the question that we can ask is, does this have to happen? Right? So this is still possible. So this was part of the motivation for the definition of a maximally psi epistemic model. Now, the literature on this is a bit confused because there are two different definitions, and nobody bothers to make the point that they're different, but they are. So let me give you the two definitions. Okay, so first of all, there are two related and equivalent definitions. They're both based on this particular explanation, the explanation for the indistinguishability of pure states. Indistinguishability of pure states should be explained by overlap of the corresponding probability measures. So this is the first definition, and it's due to Owen Moroney first. So we say that an ontological model is maximally psi epistemic 1, the first kind of maximally psi epistemic, if for all pairs of pure states, the probability of getting the outcome phi, when you measure a basis including phi, when you prepare the state psi, is entirely explained by the overlap of those two regions, right? So here is the overlap region. This is the probability that psi assigns to that region. And that probability is basically the probability of getting this outcome. Okay? Okay, so this is just saying that the probability of obtaining phi when the system is prepared in the state psi, sorry, that should be psi, is entirely explained by the overlap. Cauchy-Specker model and the Speckens toy theory are both maximally psi epistemic, and you can show that maximally psi epistemic 1 implies the model is Cauchy-Specker non-contextual. So this means that immediately you take any proof of Cauchy-Specker non-contextuality and you've ruled out this kind of model. Very easy. There's the second kind, which is based on a different notion of overlap. So we can introduce the classical overlap between two probability measures. This is the formal definition, but basically you can think of it as the joint area under both of the graphs, right? And it has an operational interpretation. So suppose somebody prepares either psi or phi with 50-50 probability, doesn't tell you which, and then you learn the exact ontic state of the system. So you learn, okay, the ontic state is here. What's the probability that you're going to make an error? It turns out to be exactly this. So it's a linear function of that overlap. So large overlap means smaller probability of distinguishing. Okay, so that's based on knowing the ontic state, and then we can introduce the corresponding quantum measure, which is, suppose, either psi or phi is prepared, and you have to guess which, based on the outcome of a quantum measurement. You don't get access to the full ontic state of the system, you just do a quantum measurement. And in quantum mechanics, this is the corresponding overlap. For those of you who know about these things, it's just really 1 minus the trace distance. And it has the same kind of operational interpretation. So if we compare this quantum overlap with the classical overlap, then we're comparing like with like. They both have the same sort of operational interpretation. So the model is called maximally psi epistemic type 2 if all pairs of pure states, the classical overlap and the quantum overlap are the same. So again, the probability of incorrectly guessing which state was prepared is entirely explained by the overlap. Again, Cauchy-Specker model and Speckens toy theory are maximally psi epistemic 2. As far as I can tell, there's no implication either way between maximally psi epistemic 1 and maximally psi epistemic 2. And maximally psi epistemic 2 does not seem to apply Cauchy-Specker non-contextuality. So I can't just say, okay, Cauchy-Specker contextuality rules this out. But it turns out you can still use non-contextuality inequalities to help rule out this notion. Okay, so let me just criticize these definitions because, I'm being kind of negative in this talk, right? I could give two versions of this talk. One which says we've proved the reality of the wave function beyond all doubt, and another one which says we haven't proved very much and there's loads to do. This is the version I'm giving here, right? So although I'm responsible for some of this stuff, I don't think these are very good definitions. So the structure of the definitions is as follows. Let's take one of the explanations from the Speckens toy theory. In this case, it was the indistinguishability of pure states. Demand that this explanation completely accounts for the phenomenon in a maximally psi epistemic model. So first of all, two criticisms. First of all, the decision to focus on the indistinguishability of pure states is arbitrary, right? Instead, we could focus on some of the other explanations. The explanation of no cloning, for instance, or the explanation for different decompositions of mixed states. You could say those are key things in epistemic models, so why don't we demand that those are completely accounted for? I could also use a different state discrimination task. I'm talking about minimum error discrimination here, but why not unambiguous discrimination, for instance? So you can basically choose any task for which you have a epistemic explanation and base a definition of maximally epistemic on that. And there's no reason to focus on indistinguishability of pure states per se, but they give different classifications of the models. In particular, this one is preparation non-contextuality. That's going to fail for even a qubit. Quotient-Specker model is preparation contextual, and so it gives a different categorization of the models. Secondly, even if we focus on state indistinguishability, in any ontological model, there's two ways in which it's explained. One is the probability measures overlap. Two is that the response functions only reveal coarse-grained information about the state of reality. You don't have access to the state of reality. You only have access to the results of quantum measurements, which, even in the Spekens toy theory, don't tell you the exact ontic state. So the question is, should this explanation play no role in the epistemic model? Okay, so Spekens toy theory, as we saw, was based on this assumption that you can only know half of the available information. The fact that you can only know half of the available information implies that the measurement response functions must be coarse-grained. They cannot tell you the full ontic state, because otherwise you'd know too much. Okay? So they must be coarse-grained. So we expect in epistemic theories that the response functions are coarse-grained. Now, it happens as a really sort of an accident that in the Spekens toy theory, you're still maximally epistemic. It happens that this doesn't matter in this particular theory. But in general, there's no principled reason from a epistemic point of view why coarse graining should play no role. Okay? So why do I care about maximally epistemic? The answer is I don't. So in light of this, this is all I really care about. Okay? I want to show that there must be pairs of states in the ontological model such that the classical overlap is small, but the quantum overlap is large. Let's try and make epsilon and delta as small as we possibly can. So that's the task. If I find families of proofs for which epsilon and delta can both be made to go to 0, then I will have a proof of psi ontology. Okay, so this is the subject of overlap bounds. I'm going to be very brief here because I know I'm running out of time. What we do in overlap bounds is we usually consider some set of states and another state which we're going to compare them to. Then we compute the average overlap between the states in the set V and psi. Note that I can have an arbitrary probability distribution here. I just want this to be able to be interpreted as an average overlap. It doesn't matter what the probability distribution is. Right? So I can choose these with different probabilities. And then most works use this to provide a bound on the ratio of the classical overlap to the quantum overlap. This is a really bad idea. Again, I'm criticizing my own papers here because that's what I did. Because the thing is, it's not going to show this, right? This could be 0. This could tend to 0 if both LC and LQ tend to 0, provided LC tends to 0 faster. So really, if you want a proxy for what we want to look at, you want to look at the difference between these two. If this is close to 1, then you really have what you want. So we can look at the overlap bounds that have appeared in the literature and look at, so these are the dimensions that they exist in. This is the number of states they involve, and these are the overlap. These are the overlaps. And so basically, these two proofs, the one that I did and Amaral et al., these are straightforwardly based on non-contextuality inequalities. In fact, Barbara Amaral doesn't even know that she has an overlap bound because they just propose this as non-contextuality inequality, but it turns out to be quite good for this task. So those are the numbers, but what we want to do is optimize the difference. So what we can do is compute the overlap deficit, and then optimize it over the number of states and dimension in the proof. And when you do those optimizations, this is what you get. So as you see, the Amaral et al. Proof is the best. It tells you that the overlap deficit has to be at least 0.3 or so. But this is kind of a non-constructive proof, and I only guaranteed that in very high dimensions with very high numbers of states. Okay, otherwise things look pretty bad because I wanted these to be close to 1 and they're nowhere near. There was an experiment done. One experiment has been done on these overlap bounds. It was by Andrew White's group in Australia, and that was based on the Branchiard result here. And this is what they obtained. So K, we're not really that interested in, but the experimentally confirmed overlap deficit is 0.047, really small. Could do better than that, right? In fact, even the Barrett et al. Proof, which is in Hilbert space dimension 4 and involves only 16 states, could, in principle, give us a better number than that. Not by a huge amount, not close to 1, but if you want to do an experiment that beats Andrew White on something, that's something that can be done. Okay, so we can get a larger one from the Barrett if we did an experiment on Barrett et al., but we would really want this to go to 1. Okay, since I've run out of time, I was going to spend some time explaining how you prove those things, but I'll leave that. Let me just go to the conclusions. So first of all, some related work. Okay, so you can prove overlap bounds in slightly different frameworks. So first of all, we've been talking about prepare and measure, but obviously there's dynamics as well. So if you look at how unitary dynamics or collapse postulate, this is what paper was referred to in the previous talk. You can derive overlap bounds based on that as well, although actually none of them are as good as, so far none of them are as good as this one. Okay, so, but there may be other things that can be done there to get better overlap bounds. We can also consider higher order overlaps and things like that. So there's actually a number of posters at this meeting which have considered overlap bounds of various types. So by higher order overlaps, I mean, instead of considering the overlap of 2 states, you consider the overlap of 3 states or 4 states or so forth. As far as I can tell, you can't use those results to prove better pairwise overlap bounds, but they're nonetheless interesting directions to look at. Okay, so just to summarize, there are several bounds that show K goes to 0, but it's much harder to get this overlap deficit close to 1. Best we've done so far is 0.3. Any non-contextuality inequality of an appropriate type. It's not all non-contextuality inequalities, but it's a family of non-contextuality inequalities, can provide an overlap bound. So if we can find a non-contextuality equality in that set that has a deficit close to 1, then that will be a way of proving what we want. And I don't have any reason to believe that doesn't exist. In fact, my conjecture is that that does exist for a sufficiently high dimension Hilbert space. There's some open questions. So if you really want to do experiments on any of this stuff, we need error analysis. There is an error analysis for the Barrett and Branchiard style of proof, but not for the other kind. Really, we want to try and get this as close to 1 as possible. I'm still optimistic that it can be done. So my conjecture is that infinite dimensional Hilbert space quantum mechanics has to be psiontic. That's basically my working conjecture. So that's what I'm trying to prove. Also, the implication between contextuality and non-maximally psi epistemic only goes in one direction. So there might be overlap bounds that you can get that don't follow from non-contextuality inequalities. And that would be interesting because that would put us in a sort of new regime. And then investigating applications. So since I'm over time, I'm going to stop here. I do have some slides which you can ask me about in a discussion session as to what are the implications for our interpretation of quantum mechanics from these psi ontology results. But that's something that I imagine that we'll probably talk about in the discussion session. So thanks for your attention. Okay.
All right.
Thank you very much. Now it is the tea time, and we again reassemble at 11:30 for the questions. And the questions will be, again, has to be deposited to Dr. Ritesh Singh.